Our final chapter, and in terms of what you're going into, if you're going into study level 7, this is an important chapter. A lot of the things in this you will be using in level 7. Okay, so we're going to have a bit of a revision first. I'll probably go through, well, I can't go through this too quickly because I know the module that you did last semester was, the pace was relentless, and I don't know how much time you spent on integration. So I'm probably going to actually take my time on this, which would make the lectures this week longer than I wanted, but so be it. Yeah. So let's see. So if a real valued function is positive between a and b, then the integral is defined as the area under the curve. Now you can make this very, very rigorous, but that's something we won't quite go through. So this thing here, this integral, this funny thing here, if the function is positive, is defined to be that area. You can use something called the second fundamental theorem of calculus. You can learn how to calculate these things, and you learn that there's a link between integration and antidifferentiation. Now, basically what we're looking at is there is a relationship between them, and we'll see what this is. So for example, say if we look at x squared, and we can differentiate it, call it d dx, 2x. So that's an operator or a transform. I think an operator is probably the best way to talk about it. So it takes an input, which is a function, and outputs another function of x. So anti-differentiating is doing this in reverse. And for the moment, we could write something like d dx inverse of 2x is equal to x squared. Now this is just for the moment, because eventually this is not going to be the whole story. But this is anti-differentiating, and it says it is running differentiation backwards. So you start with x squared, you differentiate to 2x, and it seems like you can anti-differentiate back. So you differentiate x squared, the derivative of x squared is 2x, the antiderivative of 2x is x squared. So this actually isn't the whole story. And it isn't the whole story. Actually, there's a nice little aside here. If we remember from our matrices, so if you had something in terms of matrices that sent, say, two different things to 0, then the matrix is not invertible. We actually, strictly speaking, have a similar story here with differentiation, because you can have multiple things that differentiate to give you 2x. So x squared plus 3 has a derivative of 2x, x squared minus 4, and all of them of the form x squared plus c. So what we're actually going to do, this inverse isn't going to be a perfect inverse. We're actually going to say, okay, the antiderivative, which we're not going to write as d dx inverse, isn't going to give us a single function, but it's going to give us a whole family of functions. Okay, so instead of saying 2x, you're going to go with x squared plus c. Now the thing on the left isn't a single function, but we don't have to worry about that too much for now. Okay, so this is where this extra constant comes from. So if you want to say what has a derivative of 2x, you get loads of things, x squared plus a constant. There's an infinite family of solutions to that little problem. So this is usually called the constant of integration. I would call it the constant of anti-differentiation. So just to be clear, you might say, oh, he's talking about integration, anti-differentiation. When there's the limits like this is integration, and I call the process of undoing differentiation anti-differentiation. Okay, so we can think about the antiderivative of 2x as x squared with no c, because all of them differ by a constant. Okay, so here what we have is, how am I going to write this down? I'm not sure what this equivalently is all about. So anyway, The second fundamental theorem of calculus says if you want to, I know what the other way is going to be. Integrate from A to B. Yeah, I know what the equivalently is going to be. Okay. It says antidifferentiate. So go from the derivative back to the original function. Now here, this is a scenario where you don't have to put in the plus c. It would just disappear. So you can just, I think we're going to see this down below. Okay. So this is what you write. You antidifferentiate and then you evaluate at the top limit minus evaluate at the bottom limit. And that this gives you the correct answer is called the second fundamental theorem of calculus. So this is just another way of writing exactly the same thing. So I'm saying that the antiderivative of little f is big F. And then you do top limit minus bottom limit. So in other words, to calculate an integral, find an antiderivative, and in fact, any antiderivative will do, so there's infinitely many, but any will do, as we'll see in a minute. Then substitute the top limit minus the bottom limit. So to calculate the integral of f, we need to be able to antidifferentiate. So I think, so say if you want to antidifferentiate f, which would be over actually here, be careful, let's make it consistent. So you got little f here, and you want to antidifferentiate it to big F. So in other words, you want to find a big F that differentiates to give you f of x. That's what antidifferentiation is. And we're not worrying about the plus c, as we'll explain. We said earlier it doesn't matter which antiderivative we use because there's loads of them. For every constant, it can be shown that all antiderivatives of a function f differ by a constant. There's a little tiny bit more to it, basically that. So they're all of the form f plus a constant. So the thing is, so what if we use, instead of say x squared, we use x squared plus 2? Well, let's see what happens. So suppose we're integrating from a to b f of x dx, and suppose that big F is the antiderivative of little f, and suppose we use big F plus c. So you get f of x plus c from a to b, and you do top limit minus bottom limit. So you get f of b plus c minus f of a plus c, and what happens is you get a c minus c. You end up with big F of b minus big F of a, and so there was no point in using the same thing. Yeah. So therefore, all in all, we need to be able to antidifferentiate if you want to calculate integrals. Okay. Now, for various different reasons, we don't actually use this ddx inverse notation. Instead, this is the symbol for antidifferentiate with no limits. You can read it as antidifferentiate with respect to x. This is how it should be read. It isn't exactly an operator because it doesn't go from function to function. It goes from function to family of functions. It makes a little bit of sense to write something like this. Okay. Okay. Now, what we have is an issue is, say you're doing integration, you have to do antidifferentiation. It's just to kind of show the difficulties of integration and all the different methods you have. So the first method that we would have is called a direct method, which it doesn't even appear on this thing. I will be going through all these. Then there's a manipulation, which would include partial fractions, which you should have done last. Partial fractions. We're going to be doing something new called complete the square. Okay, and other manipulations, which we'll be talking about very soon. So that's the second way. So direct is just very easy. Like if you're anti-differentiating x squared or something like that, it's very, very easy. The second is the manipulation, where you have to use some kind of a technique to rewrite what you have. And we'll talk about that in a second. The third technique is substitution. And you would have done that last semester. We'll be looking at it again. And another new thing that we'll be looking at is integration by parts. Now, so the new things we're going to be doing are complete the square and integration by parts. So they're new on top of what you're supposed to already know from before. And they're both useful if you go into level 7 maths engineering. Okay, so here we see that basically integration is harder. And the strategy I'm going to do the 4-step strategy, but you can actually, in fact, do way more. Now, even if I'm looking at this, I Cauchy's formula, I'd probably have a stab at. Yeah, okay. Whereas differentiation is very, very easy. Okay. So this is the strategy that we're going to look at. So you've got something you want to integrate, you need to anti-differentiate it. So the first thing is, can you do it in the tables? From the tables directly, we'll describe what that means. The second thing is to do manipulation, and we'll look at some particular manipulation. So this is the thing that you're trying to anti-differentiate is not quite in the table, so we need to rewrite it. Some techniques include partial fractions, which you possibly did last semester, which are important if you go into level 7. And complete the square is something new that we're going to do. Substitution, which again is something that you should have done last semester, but to avoid confusion, we're going to call it W substitution because there's a U substitution in what's called integration by parts. Okay. So historically, integrals were calculated long before anti-differentiation was even a thing. Basically, what I'm saying here is that there is you've done some differentiation. So if you run differentiation tables backwards, you get antiderivatives. So the antiderivative of 3x squared is x cubed, antiderivative cos x is sine x, antiderivative 1 over x is log x, etc. So they're considered easy. Okay, usually such derivatives will be presented in a table of derivatives. Okay, and if you run them backwards, yeah, that's what we just said. So a lot of them can be, also you can just look on your derivatives and run them backwards. Now the 3 functions that people assume are not in the tables and attempt to use more sophisticated than necessary techniques, so they'll try and do usually manipulation or substitution, is these 3. So keep an eye out for these 3. They are in the tables. The first one is an inverse tan, the second is an inverse sine, and the third one is log of x. All of them are in the tables. And because integration is linear, we can anti-differentiate, or it's because differentiation and anti-differentiation are linear, we can anti-differentiate term by term, fixing constants like we did with partial differentiation. You can use a single c when you've got a sum. Now you can have loads of c1s and c2s, but they just, yeah. Okay, so let's do some examples. So have I got space? Where am I doing this? Okay, so the first thing, so I'm looking at this anti-differentiation. So I'm going to fix constants, so I'll be fixing the 2, the 3, and the -2, and anti-differentiating what's left. For the powers of x, I have add 1 to the power, divide by the new power, that's the thing down the bottom. The antiderivative cos of x is sine of x, and antiderivative e to the x is itself. So fix the 2, antiderivative x cubed, add 1 to the power, divide by the new power, plus fix the 3, antiderivative cos of x is sine of x. Fix the -2, and the antiderivative of e to the x is itself. And we could tidy that up a little bit. We could do the 2 over 4 as a half. Maybe we'll do that. And because we're anti-differentiating, we need to do plus a constant. Okay. Second one, 4 over x. What are we going to do with that? So this is a small bit of manipulation. 4 over x is 4 by 1 over x. Now, if I asked you, what is this? Now, if you said 2 over 3, that's what it looks like. But what it is 2/3. 2/3. 2 by 1/3. And in general, a over b is equal to a by 1 over b. So 4 over x is 4 by 1 over x. Okay, and then you could, so this is what we're anti-differentiating. So we'll fix this constant. So we find that the antiderivative of 4 over x is equal to, so fix the 4, And the antiderivative 1 over x in the table is its log of the absolute value of x, and of course plus c. And what is the third thing? Third antiderivative, that is in the tables. 1 over 1 plus x squared is actually of this form with a equal to 1, because 1 over 1 plus x squared is equal to 1 over 1 squared plus x squared. So we get that the antiderivative of 1 over, so I'm going to write that 1 as 1 squared plus x squared dx is equal to, yeah, so there's probably a small comment here that is worth making. So people get a bit confused about the little dx here. So that's telling you, like, remember with the partial differentiation, are you differentiating with respect to x, y, z, etc., or t or l or whatever? So this is saying that you're anti-differentiating with respect to x. When we do substitutions, that will be important because we'll be anti-differentiating with respect to w. Okay, so here we're going to use the formula that's just up there. So this is 1 over 1 inverse tan x over 1. And we can tidy that up. 1 over 1 is just equal to 1. 1 by inverse tan is just inverse tan. And x over 1 is just x. And of course, plus c. So they're all from the tables. The next kind of thing is if the things that you're hoping to anti-differentiate, that they need a bit of a manipulation, a bit of a rewrite before you can actually anti-differentiate them directly using the tables. Now, we can't list all possible manipulations, but here's some of them. So one of them is negative powers. So if you know your way around indices, you know multiplying gives positive powers and dividing gives negative powers. So 1 over x cubed, for example, is x to the minus 3. So, for example, so write if you have 1 over x to the n, rewrite this. Now, this is not anti-differentiating it. They're just equal. They're the same thing. And then you use the table antiderivative that any power of x, you add 1 to the power and divide by the new power. And this is the power rule, which is, okay, let me look at what I'm doing on the next page. Okay, and then, for example, if you're looking at, say you're looking at 1 over x cubed, so the antiderivative of 1 over x cubed, so you do manipulation, you rewrite the 1 over x cubed as x to the minus 3, and then use the power rule, add 1 to the power, so minus 3 plus 1 is minus 2, divide by the new power, and then plus c. Now you can tidy that up a little bit if you want. Now, x to the power of minus 2 is divided by x twice. So this, actually, I'm just going to leave it like that because I think some of us can simplify, but those of us, maybe I should show it. So the way I would probably simplify this is, so this x to the minus 2 is positive. Now you might say, but the negative power, well, negative power doesn't mean it's negative. Negative power means it's division, and it actually means dividing by x squared, and x squared is positive, so dividing by x squared isn't a negative thing. But the top is positive, the bottom is negative, and plus over minus is minus, so I know I have a negative thing. Now what I can do is the division by 2 is the same as multiplying by half, and in fact I can just keep the x to the minus 2 if I want. So that's probably how I'd rewrite that, but what was done previously is absolutely fine. Okay, and now I'll remind you, this is all technically revision. Okay, so if you have something like this, if you know your way around indices, you know that the mth root of x to the n, well, there's two ways you can go about it. You can say it's x to the n and know that the mth root is to the power of 1 over m. Actually, this is the only way you need to go around it. And then you know that repeated powers, you multiply the powers, and n by 1 over m is n over m. And then you can use the power rule again. So for example, if you want to anti-differentiate, for argument's sake, 1 over the cube root of x, maybe x to the 5 will make it a bit more complicated. So what you can do here is you can use what I just did above. So this is x to the 5 all cubed root, which is the power of 1/3. Now that's not ready to go yet because it's division. So you make it a negative power. Or sorry, don't make it. It is equal to a negative power. And now add 1 to the power. So minus 5 over 3 plus 1 is x to the minus 2 over 3 divided by the new power, which is minus 2 over 3. And then if I was going to tidy this up, so dividing by 2 over 3 is multiplying by 3 over 2. You get minus 3 over 2, x to the minus 2 over 3 plus c. Other things you can multiply out. So for example, if you're looking at root x times 1 plus root x, you can just multiply this thing out. Root x by 1 is root x by root x is x. And then you can write the root x as x to the half and use the power rule twice and tidy up like that. Another example, x squared plus 1 over x squared all squared, I can multiply out carefully. So I'd be doing like x squared plus 1 over x squared times x squared plus 1 over x squared, and I'd get x squared by x squared to give me x to the 4, 1 over x squared by 1 over x squared to give me 1 over x to the 4, and then the x squared by 1 over x squared to give me 1, and the 1 over x squared by x squared to give me another 1, so that would give me the 2. And then you're just using that division by x to the 4 as a negative power, and then now the 2 might catch you. What do you differentiate to get 2? 2x. Okay. The other thing, the other thing is dividing in. So look at x squared plus 1 divided by root x. So you can divide in the two root x's separately. Use the fact that root x is x to the half, and division of like powers is subtraction, and off you go. The other way is not examinable, but you can, something like this, you can divide in x minus 1. Another thing that I'm probably not going to really look at, is trigonometric manipulations. So for example, you can use formulas. So for example, if you have a cos squared, you can write it as a half 1 plus cos 2a, and both of those are in the tables. Sec by sine by cos, you can use some trigonometric identities to see that this is actually just equal to sine, for example. So this is just simplifying stuff with sine and cos and tan. What else have we got? Slightly more advanced but routine include partial fractions, which will be important next semester, and completing the square, which we are going to be doing in Math 6040. So an example of partial fractions is rewrite this complicated thing as a sum of simple things, and that's relatively easy to differentiate. An example of completing the square we'll be looking at in later on next week. Okay, so what do we got here? When we run the rules of differentiation backwards, we get rules for anti-differentiation, and W substitution comes from running the chain rule backwards. Okay, so what does the chain rule say? So the chain rule says that if you want to differentiate a function with an outside and an inside, you differentiate the outside, so I'll write that as v dashed, evaluate at the inside, w of x, and then times the derivative of what's inside, times w dashed of x. So written as a rule for anti-differentiation, we get that the antiderivative of v dashed w of x, so maybe just to reiterate, this is, I'm differentiating v of w of x, so that f dash of x doesn't really belong there. So if I'm differentiating, I'm really focusing more on the derivative of this is this, so come back the other way if you anti-differentiate. So the antiderivative of this thing on the right is the thing inside the bracket, v of w of x plus c. So that's the chain rule ran backwards. It's a perfectly good theorem, but look, the pattern is like, that's not an easy formula to use. So what we do instead is when we're confronted with the thing on the left, we let w to be w of x. Now we'll talk about how do we know how to pick the w. We'll talk about that a bit later. So you pick this w. Now last semester this would have been a u. You can still keep using u, that's absolutely no problem. I just think it's a bit easier to use w for this and then u for the integration by parts. So you got w is equal to w of x, and you differentiate both sides, and we're going to get a relationship between dw and dx. So if I differentiate both sides, I get dw dx is equal to w dashed of x. Now what I'm going to do next doesn't actually make sense, but it does give you the right answer. So what I'm actually going to do next is just nonsense, but it gives you the right answer. So I'm going to solve this for dx. So I'm going to multiply both sides by dx. I get dw is w dashed of x dx. And then I'm going to divide both sides by w dashed of x to get dx is equal to dw divided by w dashed of x. And I'm going to put the integrals back together. So I get v dashed of w of x, w dashed of x, dx. So this is going to be v dashed. So the w of x I'm now saying is w. The w dashed of x is just going to sit there for the time being. And now I'm going to take that dx is equal, and I'll probably start using some colors here that I'll probably regularly, well, I don't think we're going to have too many w substitutions, but I'll try and use this color scheme. So the dx will replace with dw over w dashed of x. And now we're going to do w dashed of x divided by w dashed of x is 1. That disappears, which is strictly nonsense, but gives us the right answer. So we get v dashed of w dw. And what is the antiderivative of v dashed of w with respect to w? Well, it's just v of w, but w is equal to w of x. So you get v of w of x plus c. So that's how w substitution actually, how we write it. Okay, so how do you know, the question is, how do you know if an antiderivative requires a w substitution? Well, in terms of your strategy, you see, is it in the tables? If it isn't in the tables, you try a manipulation, and if the manipulation doesn't work, then you'll try a w substitution. Okay, now the question, which is a bit difficult, is how do you know what to take for the w? So I've got 4 ways. The first is you see a function inside another function and a constant multiple of its derivative. That's the best way, but not necessarily that easy. The second way is you see a function inside another function. So we'll do it for all of these. Okay, and that way is a bit better. The third way is using Liate, which we'll see later on in this week's lectures. And the fourth is just try something. Usually there's just 2 options. If the first doesn't work, start and try again. Okay, so here we'll have a look at this one. So first of all, I recommend you do direct. So nothing as complicated as this is in the tables. The only thing you could do in terms of manipulation is to say that the square root is to the power of a half, and dividing by power of a half is a negative power. So you could manipulate this to x plus 2 times x squared plus 4x. Now, if you don't do this manipulation, you'll have to do it later, but actually the manipulation later is if you do it later, it's a bit easier, so don't worry too much if you didn't see this. But there's nothing else you can do here. You have to be wary as well not to do things that don't make any sense. You can't multiply in that x plus 2 because of the power of minus half. It doesn't make any sense. So we've nothing left to do. We should try a w substitution. So let us give, well, the fourth reason is try something. So that isn't a reason. So we give 3 reasons that you try x squared plus 4x. So the first is, this is going to be our u. It's inside something else, inside x to the minus a half, check. And we have a constant multiple of its derivative. Its derivative is 2x plus 4, which is a multiple of x plus 2. So that says you should definitely use w equal to x squared plus 4x. The second way of saying it is you could say it's inside the x to the minus a half. And if you didn't have the x to the minus a half, go back to the original, you see that it's inside the square root. So it's certainly, it works on that level. And then by Liate, so Liate says, we'll see it later. So if there's any logs, you pick the w to be the log. There's no log here. Inverse trig, there's no inverse trig here. Algebraic, yes. And Liate says pick the highest power. And you've got x squared plus 4x versus x plus 2. Now you might say, oh, well, I just pick x squared. In general, you're going to take as much as you can. So you pick a higher power. So we're going to proceed with w equal to x squared plus 4x. And let's see how this goes. So let's start putting this thing back together. So you get the integral of x plus 2 can just sit there for the time being. The x squared plus 4x is our w. It's to the power of minus a half. And now dx. Now what we need to do with the dx is we need to get a relationship between dx and dw. So take w is x squared plus 4x and differentiate both sides. So you get dw dx is equal to the derivative of x squared is 2x plus fix the 4, the derivative of x is 1. And we want to solve this for dw. So multiply both sides by dx to get dw is equal to 2x plus 4 times dx, and then divide both sides by 2x plus 4. So get dw divided by 2x plus 4 is equal to dx. And we're going to replace this dx in terms of dw. So the dw, or excuse me, the dx is dw divided by 2x plus 4. Now it's a little tricky here. Unfortunately, you have to notice the relationship between x plus 2 and 2x plus 4. It's not a particularly easy one, I'll be quite honest with you. So what you have to see is that the 2x plus 4 is twice x plus 2. And then you can divide above and below by x plus 2. And x plus 2 divided by x plus 2 is 1, that's gone. And then you've got this is not really a 2, this is a divided by 2, so this is a half. And that can be taken out as a constant. So you get a half. So that's the divided by 2 is multiplying by half, and multiplying by half is a constant. We can fix that by taking it outside. That's fixing it. X plus 2 divided by x plus 2 is 1. 1 by w to the minus a half is w to the minus a half dw. And now we have something that we can anti-differentiate, because we've got anti-differentiate w to the minus a half with respect to w. It's add 1 to the power, so minus a half plus 1 is a half, divided by the new power, which is a half. Now on the bottom there, you've got 2 by a half, and that's equal to 1. So if you do top, bottom, you get 1 by w to the half is w to the half, and 2 by a half is 1. And w to the half divided by 1 is just w to the half. Now what you need to do now is, you're asked to anti-differentiate originally with respect to x, so you need to put the w back in terms of x and also do your plus c. So the w was 2, sorry, there's not 2, it's x squared plus 4x, that was your w, and then do plus c. If you want, you could go back, write the power of a half as square root of x squared plus 4x if you wanted, but it's perfectly okay as it is. Okay, so that's a w substitution. Let's see another example. So this isn't in the tables, it's too complicated. The only apparent manipulation would be to write that you've got division by 1 plus x squared, which would be 1 plus x squared to minus 1. That's probably all you could do here. Okay. If you don't do that, it's not the end of the world. So say in this one you didn't do the manipulation, then back here the only difference would be that you'd have 1 over the square root of w. So and then so I'm saying that if you didn't do this manipulation here to write the 1 over the square root as to the power minus half, it's okay. You'd end up doing it back here. You'd have the 1 over root w there, which would be 1 over w to the half, and division of a power is a negative power. So similar story here. If you don't do this manipulation, it's okay. In fact, I think here it makes the manipulation worse. So we're going to do a substitution. There's 2 good reasons to try inverse tan, over anything else. So there's 2 good reasons. So it's inside the exponential function, and although it doesn't look it, if you rewrite this as e to the inverse tan of x, and divided by 1 plus x squared is multiplied by 1 over 1 plus x squared. So this is something we've seen a few times now in terms of your algebra. 2/3 is 2 by 1/3. A number divided by another number is the first number times 1 over that number. And here you have a function, inverse tan, and that's its derivative. So that says that you should pick as your w inverse tan of x. That's the first reason. The second reason is that Liate. So we'll see Liate a bit later. So the first is logs. There's no logs here. Inverse trig, yes, you should let the w be the inverse trig. That's the inverse tan. The second way doesn't really work because 1 plus x squared is inside something else and also inverse tan. So you could just chance your arm. You could try 1 plus x squared. It won't work. I don't know, do we look at what happens? Oh yeah, we'll look at what happens. We'll do that a little bit later. So we try substitution. They're the two reasons. The second way doesn't work great because there are two functions inside another. In this case, you try them. We'll just see what happens, I think, if you do the wrong w. If you do w is equal to 1 plus x squared, you get dw dx is 2x. So in terms of the color coding that we've got, here's the w. And here is dx. And look, you see with the substitution, you're supposed to get kind of, I don't like the word cancellation, but essentially look, w dash of x divided by w dash of x. It kind of happened here eventually where we factored out the 2. Here it's just not working. Like, do you see that? Like, you've got divided by 2x and it doesn't work. So the mix of x and w is bad and suggests we won't be able to find the antiderivative. It might be possible though. So what you can do here is you can try and put the x's back in terms of w, but it just actually makes it even worse. So that back substitution is kind of a nasty thing. So you put, if you have the w, so equal to 1 plus x squared, you can solve for x and back substitute all those x's for w's. Now, it's because it's x squared, it's a plus or minus, so we'll just pick the plus one, and you get to here. Sure, this is way worse. So that kind of tells you, oh, look, the 1 plus whatever it was, the 1 plus x squared was the wrong one. I need to go back and use w to be inverse tan. So I'm just going to write down the integral again here. So we had e to the inverse tan of x. And if you have it divided by 1 plus x squared, it's actually easier, but we'll just keep going the way we were doing. That's what we had. So we're going to try w equal to inverse tan. So we get this is equal to e to the w. And now we're going to try and get a relationship between dx and dw by differentiating both sides of this. So we get dw dx, and we go into the tables and we see that the derivative of inverse tan is 1 over 1 plus x squared, which is good. And we're trying to solve this now for dx. So if I multiply both sides by dx and multiply both sides by 1 plus x squared as well, I'll take my time. dw is equal to dx divided by 1 plus x squared. And now multiply both sides by 1 plus x squared. I get 1 plus x squared. dw is equal to dx. So I'm going to replace this dx with this. The 1 plus x squared to the minus 1 is just sitting there. And now the dx is equal to 1 plus x squared times dw. Now, as I said, if you actually didn't do the manipulation of writing the 1 plus x squared, the division as to the minus 1, this bit would be easier because you'd clearly see the 1 plus x squared divided by 1 plus x squared. The manipulation actually made it worse. But it's right there. Look, this is 1 plus x squared, and the negative power means divided by 1 plus x squared. And 1 plus x squared divided by 1 plus x squared is 1, times e to the w is e to the w. And now you've got something that is in the tables. The antiderivative of e to the w is itself. And the original question asks us to antidifferentiate with respect to x. So we need to put this in terms of x. We go back w in terms of x. W is equal to inverse tan of x. And we don't forget our plus c. Okay, so I think we're going to do one more here, a revision. So this is sine cubed by cos x, not in the tables. Two possible manipulations. They're a little bit nasty. So one of them is you can write sine cubed as a sum. You can multiply the sum by cos, and then you can write this. So there's like sine by cos, cos by cos, and there's stuff in the tables you can rewrite products of like sine and cos as sums of sines and cos. So that's good because you learn that. Like you'll notice there's no product rule here. You can run the product rule backwards, and we will do that in the next few lectures, but it's not as easy as the product rule of differentiation. So when you don't have a product rule, what you want to, you're good with sums. So kind of understanding that if you could possibly write sine cubed x by cos x as a sum, and then you can anti-differentiate each term in a sum, term by term, that's good. But we won't do that here. Instead, what we're going to do is we're going to look at this thing, this k, this integral, as sine x all cubed cos x dx. And we're just going to say, okay, there's a manipulation, but we're going to say that like maybe that's too hard. Or we'll just say we didn't know. Okay, so two reasons to pick w equal to sine. Liate obviously doesn't work because the sine and the cos are on the same level. Now you'll see this liate soon. So the two things is you have a function inside another function, that's sine of x, and a multiple of its derivative. So you got sine and a multiple of its derivative. So that's a reason to pick w equal to sine. The other reason is that sine is inside something else. So there are the two reasons that you'd pick it. So off we go. So the integral was called k. So we're saying w equal to sine. So it's sine cubed is now w cubed. Cos x is just sitting there. And now we get a relationship between dw and dx. So we had w is equal to sine of x. Differentiate both sides with respect to x. dw dx is equal to cos of x. Divide both sides, or sorry, multiply both sides by dx. We get dw is equal to cos of x dx. And divide both sides by cos of x. dw divided by cos of x is equal to dx. And that's what's going to go in. There's a dx here. We're going to write it as dw over cos x. And now the nice thing happens. Cos x divided by cos x is 1. 1 by w cubed is w cubed. We have reduced the integral using the w substitution to something that's in the tables. Antiderivative of w to the 3 is add 1 to the power, divide by the new power, and we want our answer in terms of x. So the w is sine of x to the 4, which we could write as sine to the sine. We could put the 4 there if we want, but we won't. Over 4 plus c. Now, strictly speaking, that is all revision, but I know it won't be. It wasn't easy last semester. Yeah, so we'll see how you get on. So hopefully, like if you actually looked at the differentiation in the last chapter, the actual differentiation wasn't necessarily too difficult. It was just that it was new types of things. So we didn't really push, like we didn't have loads of chain rules and stuff, loads of product rules. If you look at it, it could have been nastier. It's going to be a similar story in this chapter. Now it's hard. There's no two ways about it, but I won't be pushed. Like there won't be too many W substitutions and stuff. But the more you do, the better. I strongly recommend going through those revision exercises.